I want to start.
So I want to start with
what I think is the simplest example I can think of to deal with how net torque and net force problems should be approached. I want to start by reminding you that we already talked about statics problems. And statics problems are not just first law problems. Statics problems are problems in which the velocity of the object is zero. The object stays in place. So although they are a set of Newton's law problems, the difference is that there are Newton's first law problems in which this is not true. The object just doesn't change its velocity or change its angular velocity, but it can be moving. Static problems were problems in which the object was at rest. Now, what we're going to deal with today are problems in which one or both of Newton's laws could be first or second. So I want you to understand that there's a lot of possibilities there, and I don't feel like listing them all out. But if you have say you have a merry-go-round and a kid or two apply forces to the merry-go-round, maybe cooperatively. I think they want it to go around and the merry-go-round begins to spin. Well, if you want to analyze what's happening to this problem, then Newton's laws can assist you here. The first thing that you should ask yourself with any of these problems is, what's the most likely outcome of what's happening? You may or may not have that. Maybe the question is to find out what the outcome is. But if you're told that a couple of kids are pushing on the outside of a merry-go-round, you likely have an idea that it's going to spin. But you probably also have the idea that it's not going to go anywhere. Like the merry-go-round's not going to suddenly shoot across the ground this way. And although we laugh, I want to remind you that that suggests the net force is equal to zero, but the net torque is not equal to zero. So it's a first law for translational motion, but a second law for rotational motion. You just follow where I'm going with this? So we're going to look at questions that are going to involve both translational motion and rotational motion. Your job at the very beginning of the problem is to try and get a handle on what you think the situation is going to call for. Does that make sense? All right, we're going to start with a problem that you've already done before in a different form, and we're going to change it just a little bit. All right, so let's, and we'll start off nice and easy with no friction. Box on the table, box hanging off the table, but a pulley there. But this time our pulley is not massless. Our pulley has inertia and therefore is considered a massive pulley. All right. So we're going to put I'm not going to put any numbers to this. Again, for most part, I want to just talk about how these problems are solved. But let's say the block hanging M, the block on the table 2M, and let's say that our pulley is a disc of radius R and mass M. So we're all multiples of the same value. So everybody follow this? So the mass of the pulley and the mass of the block that is hanging are the same mass, but the block on the table is twice the mass of those. Everybody good? Everybody understand the nature of this problem or what's going to happen? So if you're trying to make yourself a set of steps to follow and questions to ask, and I'll do my best to not get distracted, I'll try and stay on point. Can you decipher from the information presented what you think is going to happen in this problem? So let's just do 1, 2, 3. Is object 1 going to move? Yes. Okay. Is it going to change location?
Yes.
Is it going to change the direction it's going to face? Okay, so do you understand why I asked those three questions? So we're trying to decide which of Newton's laws applies to that block. And from the answers to your questions, it sounds like A, the net force on the block is going to be MA, and the net torque on the block is going to be 0. The direction it's facing is not going to change, but it's going to change location. So if I was to write this as a series of steps, I'm telling you, ask A, is the object going to change location? And B, is the object going to change the direction it's facing? You are applying first law and second law for both rotation and translation at the same time to each object. Again, you're applying first law or second law to each object. All right, let's go to the pulley. Is the pulley going to change location? No, I don't think so. That means net force is 0 on the pulley. Is the pulley going to change the direction it's facing? Is it going to spin? I think that's very likely, so net torque equals I alpha. That's for the pulley. Box on the table. Is the box on the table going to change its location? Yes, I think so. Is the box on the table going to spin? Is it going to change the direction it's facing? No, I don't think so. So again, we're going to go item by item and determine whether the first law or second law applies for both translation and rotation. That's our first step. I know it's a lot, but it's the same thing we did first semester. We just have 2 sets of rules to apply. Does that make sense? All right. We're going to do the same thing we did first semester again. We're going to try and determine a common direction that we will call positive. This is the second thing I think you should do after applying the laws, to try and determine a common direction that you will call positive for each thing that is moving. Now, this is going to involve rotation as well as translation. So I think it's pretty straightforward here. I'm really not trying to make it hard. I'm just trying to be very specific and very thorough. So I believe that we probably can all guess that under this action, this box is going to go downwards. This box is going to go to the right. And I think if the string does not slip on the pulley, you hear the phrasing I'm using there very specifically, because they will play with this, and you want to make sure. If the string does not slip across the pulley, then the pulley's motion will also be related to the block's motion. And I'm going to list all of those as the positive direction. So I am right now identifying the direction of spin that is positive and the direction of motion that is positive. All good? Okay. Now, there's an extra step that we have to do here. And we talked about it first semester, but we didn't talk about it very much. The question we asked was, is the motion of object 1 and the motion of object 3 linked together? Meaning, does object 1 move the same as object 3? So if object 1 is moving at 1 meter per second, can we say that object 3 is moving at 1 meter per second? Now, do you understand? Remember we did that in first semester? Well, this time, that question becomes more complicated. Yeah. So now the question has to be, is the motion of the pulley in any way related to the motion of the 2 boxes? And I'm driving at something very specifically. I want to know if I can say this. I want to know if one rotation of the pulley results in a motion of 1 circumference of the 2 boxes. Right? I want to be able to say that. Meaning I want to be able to say that the motion of the pulley is directly related to the motion of the boxes. Otherwise, if they're unrelated, I don't know how the motion of these things are connected. But you still should ask yourself this question. So if the string doesn't slip across the pulley, then all three of these will be true. This is the condition for rolling and for no slipping on a pulley. Those are conditions. I mean, we define rolling as the rotational rate is directly related to the translational rate. That is the definition of rolling. But it also works for things where the string isn't slipping over a pulley. Like I said, you need to ask this question when you're deciding the direction that's positive. But you want this question to be yes, they're connected. Are we all good? Now, something to be careful about. We have identified how the system moves, we've identified what's going to move, and we've identified how things are linked together. Now, we're going to do the same thing we kind of did at the very beginning of the year. We're going to only worry about the things that matter here. So I don't think all of this really matters. I think this matters for the pulley. I think this matters for the mass. And I think this matters for the other mass. Does that make sense? I think these are the things that matter. I'm probably interested in stuff like what is the acceleration of the system? How fast is the box going when it makes it to the ground? I'm probably interested in those questions. And those are all about the parts of the system that are moving. I don't care about the fact that the box isn't spinning. But the next thing we should do is go object by object and identify the forces acting on the object. We're going to start at the pulley. Not because I want to, but because something is different now than before. Can we agree, Can we agree that the pulley is going to spin in this direction based on what's happening in this problem? Okay, I want you to think just for a moment deeply about something I'm about to say, or at least try to. Net torque equals I alpha. First semester, all of our pulleys had no inertia. They were massless, so they had no inertia. But our pulleys have inertia now. That means that it takes an unbalanced torque to cause the pulley to accelerate. Now, I don't know if you know what that means, but let's consider the forces acting on the pulley right now. For example, there is a force acting on the pulley this way because the string is pulling down on the pulley. But there's also a force acting on the pulley this way because the string is pulling to the left on the pulley. We didn't do it like this before. We just cared about the string and the boxes. But now the pulley is involved. So based on Newton's third law, if there is a force upwards on this box, there is a force downwards on the pulley. And based on Newton's third law, if there is a force this way on this box, there is a force to the left on the pulley. That has to be true, Newton's third law. At the same time, there's another force on the pulley, probably something like this way. Right? That's to keep the pulley from moving. If that force isn't there, those two forces would pull the pulley downwards and to the left. So there's probably three forces acting on the pulley. And we know that those three forces have to sum to be equal to 0 because the pulley stays in place. But this force, it acts where the pulley is attached. So it causes no torque because that's also the pivot point of the pulley. Right, so when it comes to torque, I'm not going to care about it. In fact, I'm not even going to include it. In fact, in a second, I'm about to erase it. But we understand that there are three forces that act on the pulley, probably a fourth force. What do you think the fourth force is? Because I didn't mention it. Does the pulley have mass? So there's probably a downward force due to gravity. That would also act at the center of the pulley. It would also not cause a torque because we're mounting it at the center of the pulley. So for this exercise, I'm going to ignore its weight, but I'm also going to ignore that force because we know the net force is equal to 0. And I'm going to concentrate just on net torque. All good so far? Okay. That was a roundabout explanation, but there's one more thing here that's not going to be obvious. So let me make it obvious. These two tensions aren't the same. The only way the pulley can rotate if there's an unbalanced torque acting on the pulley, which means one tension has to be greater than the other tension so that the torques are unbalanced. And I know which one has to be greater. I know that this force, which applies a torque in the positive direction, has to be greater than this force because we know the direction the pulley rotates. So the only way that'll happen is if these two torques aren't the same, therefore these two forces aren't the same. This is different than first semester. First semester, we just assumed the tension was the same everywhere in the string. Well, that can't be true now because it takes some of that tension to cause the pulley to turn. So these two tensions won't be the same any longer if the pulley has inertia. That's a big thing to put in your notes. Take a second, write it down. Something to remind you that the two tensions won't be the same because the pulley has inertia. So, now that you got that down, I can go on. So I'm going to say that this is T1 and this one is T2. That means this is also T2 and this is also T1. Everything okay? All right, let's move on. Now that I've handled that, should we just go ahead and continue with what we have to do with the pulley? That feels like the right thing to do. Torques are more complicated than forces. But now that I've handled the forces on the pulley, I need to assemble the torques. Now, normally I won't do this the way you're about to see it. I'm going to do it this way only once because I think that you guys could use a little structure. There are two torques that act on the pulley. So I'm going to list them. Torque 2, torque 1. I'm going to list them vertically, but I'm doing this for the last time. I'm just going to add them together. I don't know what they equal. They don't equal 0. They equal something else. We're going to set it equal to I alpha, but we don't know what it equals. I do know that T1 is greater than T2. That's all I know. So I'm going to establish that T1 is positive and T2 is negative based on the right-hand rule and the direction of motion that we've established as being positive. I'm going to remind myself that every single torque is a distance times a force times an angle. So torque 2, the torque arm length will be the radius of the pulley. Do we all see that? That's R, the radius of the pulley. The next thing I need is the force applied. The force applied is the tension from the string, and that's going to be T1. The next thing is going to be the angle, and I need to convince you of this. It's 90 degrees for all pulleys. So again, every pulley will have a string that comes off of it that's tangent to the pulley, which means perpendicular to the radius. So that means this. I can just write this down real quick. So I've assembled my torques. Again, I'm probably not writing them out like this ever again, but I'm just trying to be thorough for all of you who are new to this. But this is just going to be RT2 minus RT1. That is the net torque portion of Newton's second law. Now, there's the other side of this. This is what we're doing to the pulley. Then there's going to be what happens to the pulley. Ready to go handle that side? It's I alpha, but what is the shape of the pulley? I think a disc makes the most sense. So we'll use a disk for this. It could be anything. They could have mounted a ball on there or something, but let's use a disk for this, okay? So we'll say it's a disk, and we'll say it's a disk which has a mass of m and a radius of r, so a disk is 1/2 mr squared times alpha. All right, we're done. That is the net torque equation. We've handled the assembly of the torques. We've handled anything we've had to do that has to do with the moment of inertia. This one was easy. We didn't have to assemble anything. We didn't have to use the parallel axis theorem. We just had to use a pulley, which was a disk. So any questions about that? All right, so the rest of this should be a no-brainer, right? Like, I'm not even going to write free body diagrams or anything. We're pretty sure that the rest of this is stuff we've already done. For example, I'm going to do the block that's hanging. Net force equals MA. Sure does. mg minus T1 equals MA. Right, we've done that before. I don't feel like I have to spend a lot of time on it. We're just going object by object and using whatever law we decided we have to apply. That's the step. We're assembling each of our net force equations or net torque equation. The one on the table, T2 equals 2ma. I'm not going to worry about up and down. There's no friction, so I don't care about the normal force. Any questions about what I've done? Every object with inertia should generate a relationship. Every object with inertia should generate a relationship. We have 3 relationships. Now, you've reached the end of Newton's laws again. All Newton's laws can do is generate a set of relationships that might be able to be used to determine the size of an individual force or the size of an acceleration. We have generated 3 of these relationships. Just like before, we have internal forces, tension, and we have external forces, weight. Just like before, we have something that's going to represent the inertia of each portion of our system. And there's a result. The system accelerates. So any number of questions could be asked next. What is the tension of the part of the string that's hanging? What is the tension for the part of the string on the table? What is the acceleration of the system? Right? Those are all the kinds of questions you should expect. Let's go ahead and answer what I think is the most likely outcome. What is the acceleration of the system? Is that a good question for us to ask? So let's go there. I can ignore the picture now. I'm going to grab my relationships and kind of put them off to the side someplace where I can focus on just them. I had T2 equals 2ma. I had mg minus T1 equals ma. And off to the side here, I had RT1 minus RT2 equals 1/2 m r squared times alpha. I want to find the acceleration of the system. That's this and kind of that. Kind of. Right? That's not A, that's alpha. Is there a way that I could replace alpha with something related to A? So you understand why we asked the question earlier about is there a way to relate the acceleration to the angular acceleration? And there sure is. By the way, this is almost always worth a point on the exam, doing what we're about to do. We're going to substitute, right? We want to get something that's in terms of A, or we want to substitute in terms of alpha. We want everything in terms of one version of the acceleration. So I've decided to use the linear version of the acceleration. Now, you want this next thing to happen. You're hopeful that it will. You guys are smart. You guys can see algebra, right? Do you notice that all the r's cancel out? Okay, that is very likely to happen. And here's why. Justification. The thing that's causing the torque is related to r. Right? If r was bigger, the torque would be bigger. The thing that's causing inertia is related to r. If the object were bigger, its inertia would be bigger. But if its inertia was bigger because r was bigger, we'd also have larger torque, which would turn it easier. So this is why the r ends up not mattering. Now that leaves just the motion of the object, but the motion of the object is also related to r. That's why r ends up canceling out. That's the physicalness of the system. It's not always true. If the example I gave a moment ago, where the r for the pulley was different than the r for the object, it wouldn't cancel out. It cancels out because we're on the outside of the object. It determines the torque, and it determines how fast the objects move. That's why it cancels out. It's just a nice coincidence. Like when the mass cancels out. Isn't that a nice coincidence as well? So, all the r's cancel out. I'm left with T1 minus T2 equals 1/2 ma. Well, I hope you see that if I put this over here, I have three relationships that share the same three unknowns. Your torque equation is almost always going to bridge both of your other parts of your problem together. You'll notice that it has both tensions in it. It has to. The pulley connects both masses together. That's what ends up being there. You guys good? Now, I don't know how you want to deal with this. I'm going to deal with the way I've been dealing with it all year. I'm just going to add all three equations together. Because when I do that, I have a negative T2 and a positive T2, a negative T1 and a positive T1. Are we, I heard some scuffling. Are we like not seeing how the r's cancel out or something? Do I need to do algebra? Okay. So I'm going to add all these together. The left side just becomes mg. The right side becomes 2m plus m plus 1/2 m all times a. Everybody good? Please look closely here so that I can show you some. Obviously, the unbalanced force was still the weight that was hung off the table. This has to represent the inertia of the system. Remember, if the pulley had no mass, this term would be gone. Right? If the pulley had no mass, and we would have been left with what we were normally used to, the mass of the two blocks. But obviously the mass of the pulley lends inertia to the system. Do you see how the 1/2 appeared here? That 1/2 was what? That was the 1/2 that's part of that coefficient for what the moment of inertia is. Telling you that the whole mass doesn't count, a portion of the mass counts to the overall inertia of the system. Obviously, if I replace this with a solid sphere, I bet a 2/5 would be there. Hollow ball, 2/3 would be there. A ring, just 1 would be there, right? That's where that shows up. But that's the inertia of the system, and we get the acceleration of the system here. These problems are very similar to before, but you should always be able to stop here and see the inertia of the thing that's rotating just appears one more thing on the list. If it doesn't, you've made a mistake someplace. I think this problem is largely done. Would you agree? We can solve for A and get an answer, but that's really, we can move on to something different. Because I want to show you another example, and I think I have enough time for us to look at this next example. It's a good one, and it's one that is in your homework. So I want you to see it, okay? It is a classic question that I often refer to as the ribbon question. It's never on the AP exam anymore, because once it's on the AP exam once, there's no reason to ask it again, because it's the same exact problem every time. They modify it though, they change it, they do little things to it to make it, to hide what it actually is. But it's the ribbon question. So in the ribbon question, we generally treat usually it's a disc. So they'll say it's a disc with a ribbon wrapped around the outside of it. But it could be a hoop with a ribbon wrapped out the outside of it. I can't even talk. It could be a hoop. It could be anything round. I'd argue that the toilet paper is closer to hoop shape than it is to disc shape. Would you guys agree? In fact, if you do what I just did and just rip the toilet paper off and do another sample, I bet it's becoming more and more like a ring and less like a disc. Would you agree? Yes. This is mechanics. We'll have to explore that a little bit. But we're going to do the disc question. We're going to make two assumptions. Assumption number one, the mass doesn't change as it falls. And two, the radius doesn't change as it falls. That won't be true of the toilet paper, but it can be true right here. Got it? All good? All right. We're going to start this problem by doing the same thing we did before. Do we have an understanding or an idea of what this object is going to do? You just saw it. So can we agree this object is going to change location? Okay. So I'm going to decide, yes, it's going to change location. It's going to go this way. And I'm going to make this the positive direction. All right, next, is the object going to spin? Is it going to change the direction that it faces? Yeah, very sure. It's going to spin. I'm going to make this the positive rotational direction. So I am very confident that this is a net force equals ma problem and a net torque equals I alpha problem. Right? Both things are going to happen. It's going to speed up falling down, and it's going to speed up spinning up. Do you think the rate at which it spins is directly connected to the rate at which it falls? Like, is one rotation of the disc going to amount to one circumference moved? Yes. I think so too. So I think we can say before we even get too far into this that A is going to be equal to alpha times R. And this has to be true. The ribbon is rolling. So it's clearly rolling without slipping. If it slipped, that meant the toilet paper ripped. Let's go ahead and treat this as a disk with a radius of R and a mass of M. And let's find out what the acceleration of the system is. Let's start by labeling our forces. So name a force acting on the toilet paper. Gravity. Yay. Name another force acting on the toilet paper. Tension, that's what I would use. I'd use T for tension. I'm going to intentionally make the T arrow smaller than the mg arrow because it accelerated downwards, so the net force had to be downwards. So net force will be mg minus T equals ma. All right, let's do the net torque side. Before we do the net torque side, with the pulley, it was pretty clear where the pivot point was for the pulley, right? Because it was mounted. This is not mounted, so where do you think the pivot point is? Okay, so I'm going to say this out loud, and I want to make sure you get it down. There's the real pivot point, and there's what you think the pivot point is. So a lot of people think the pivot point is at the center. It didn't pivot there. It pivoted here. Because that point isn't moving with respect to the rest. But this is an aside. You should write this into your notes. It's very important. Ready? For objects that roll, either location can serve as your pivot point. For objects that roll, either location can serve as your pivot point. This class, the overall vote was to use the center. We're going to use the center. All good? I got 2.5 minutes. I want to finish. So hear me out. Pivot point at center. 6th period is going to do the pivot point at the edge. They don't get a choice. I'll let you guys pick because you guys are doing awesome today. So we're gonna. I know I make fun of you guys, but I really enjoy my afternoons with you. Just so you know. So don't get too. I'll be just as big a jerk on Monday as I normally am. So don't get too excited. There's only one torque that acts on this. Do you guys see it? Because there's only one force that's not at the pivot point. So can I just real quickly go R times T, and that's our net torque? And it's a disk, right? So is it okay, 1/2 mr squared? And look, I want to save time. Can we just go ahead and a over r it instead of putting alpha there? Right. This is going to be something you do all the time. So all of those steps, just start connecting them. Don't be automatic about it. Make sure you thought about it. But this gets me to cancel out all the r's right away. And I'm left with t equals 1/2 ma. We're kind of done, right? 2 equations, 1 internal force. This seems pretty straightforward to me. So how about, and we've done one like this before. Can we just add it up? So t's cancel. I get mg equals 3/2 ma. I just went ahead and add them together. It's just all the stuff. Now, I can cancel the m's. And I just get A equals 2/3 G. This is a classic question. Obviously, the 1/2 is still buried in here. If this were a ring and not a disk, this would be not 2/3, right? It'd be different. It'd be a half because we would have gotten 2m there and not 3/2 m. So it would be slower. All right, folks.